Okay. Well, hi all. We're in the middle of calculus class here, and it just occurred to me that it'd be nice to videotape this. We're reviewing. We went over this on Friday. We were finally given the name of these things: the upper sum, lower sum, and such. They're called the Riemann sums, named after the mathematician named Riemann, who came up with these. They're a way to estimate the area under a curve with an irregular shape. If it's curvy, there's no geometry formula for it. So we cut it into slices and use rectangles. You can use, like here's the boundaries of the first slice. You can always use the upper of the two, which will give you what's called the upper sum, which is too big. You could use the lower of the two, which will give you the lower sum, which is too low. You can use the trapezoid sum, which means cut straight through, take these two boundary points and just connect them. And that'll give you a fairly accurate one. It's much better than these two. And you get the trapezoid sum by averaging the upper and lower sum, add them up and divide by 2. And then the fourth is, if you go halfway through the slice and find out by hand what that height is, like, let's just say this is 0, 2, 4, 6, 8, and this would be 1 because it's halfway through. You'd find out what the height of the graph is at 1 and use that. So if you find the midpoint heights, and add them all up for the rectangles. That should give you a fairly accurate estimate. How do you get better estimates on this thing? You cut it into more slices. The more slices there are, the less wasted space there will be. Like if I just did one slice, I just did one big honking upper sum, there'd be a huge amount of wasted space. Too much. If I did a lower sum, it would be a whole bunch of stuff that isn't covered. So the more slices you have, the less wasted space you have. So if I had like 5,000 slices, it would be a very close estimate. Probably good enough for our purposes. So let me try a real one. Let's say, example, f of x equals negative x squared plus 9. And I want to limit us to the interval from -1 to 3, including the 2's. So what does that look like? And I want to find the area under that curve. And what does it look like graph-wise? Actually, can somebody help me out with this? What shape is this?
Parabola.
Parabola.
Upside down.
Yeah, it's an upside-down parabola. Where's the vertex?
9.
Yeah, what direction?
Up.
9 spaces up. Did it move left or right?
No.
Apparently not. If it'd be parentheses x minus 3 or something like that, then it would move. 1, 2, 3, 4, 5, 6, 7, 8, 9. So a vertex and 0, 9. What's the pattern for a normal parabola? Over 1, up 1, over 2?
Up 4.
Up 4 normally. Over 3, up
9.
9. What's this one do?
So just the down.
Yeah, it's going down. It's the same same height, but it's going downward. Over 1, down 1. Over 2, down 4. This is the height of 9. This is the height of 8. So 1, 2, 3, 4. So this would be a height of 5. Make some nice big dots here. Then over 3, down 9. So if you're already up 9, right? Need to draw my 9 parabola. Then you'll actually hit the x-axis. That's called super lucky. or you somebody designed the problem that way. So this way. So here's your downward. Oops. Don't drink and graph. Your downward parabola. But I'm only using from -1 to 3 on the axis. So from -1 to 3, I want to draw a line here. Pretend that's straight. And here. So I want to get an estimate of this area. What I would like to do is find 4 different Riemann sums for this. I want to find the upper sum, the lower sum, the trapezoid sum, and the midpoint sum. And I need to tell you how many slices to use. The more slices, the better our estimate. But for our purposes, I'm not going to kill you. You notice if you have like 1,000 slices, it gets really complicated. Because it's kind of like, split this into 1,000 pieces, how far over is the next slice?
Like 0, 0.
Yeah, it's like negative point something. This is like 4 spaces, so it'd be like 4 thousandths. So negative 0.996. And then you plug that in to get the height into that. So negative 0.996 squared, which is positive, then make it negative again, and then add 9. I'm going to make it easier. I'm going to make n equal, n is the number of slices. I'm going to make it equal to 3. Oh, wait a minute, no, 4. 4. Why? Because that means each slice is 1 unit wide. You're welcome. Let me first make my drawing line, dotted things there. That kind of make sense? So there are 4 slices, 1, 2, 3, 4. And they're nice and even as far as like, they're 1 unit, 1 inch wide. All we need to do is find the heights. And given the diagram we have, you can probably do it by hand.
Yeah, you could.
So you're going to have to add 4 numbers together to get your estimate. The height of this, 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 and this times the base. So each one's going to be a rectangle. Look at the very first slice from -1 to 0. If I did an upper sum, what height would I use?
You would use 9.
Look at the 2.
9?
Yeah, you have either 8 or 9, and the upper of the 2 is 9. So what I'm going to do is, remember, a rectangle is always base times height. Whenever you take the area of a rectangle, it's always base times height. That's why we use it, because they're easy. So I'm going to get the upper sum, which is 1 times 9. That's the first slice. Okay. Oh, I don't know if you can see that from there, but it just says first slice. So 1 times 9 plus, look at the next slice, the one from 0 to 1. So the width of, so the base is 1. What's the height of the second slice? Leland, take this. What's the height of this next slice if you take the upper of the 2? 9, because it'll be either 9 or 8. This is another 9. Leo, take the third one. What's the height of this third slice?
8.
8. It would either be wow. It would be either 8 or 5, and we'd take the higher of the 2. So 1 times 8 plus, and now take the last one. What's the height of the last slice? 5, right. We have either 5 or 0, and we took 5. Now understand them up. So it's 9 plus 9 plus 8 plus 5. It's 18, 26, 31.
Mm-hmm.
That's our upper sum estimate of the area underneath that curve. Again, it's not going to be perfect. And it's probably going to be off by a bit. But it's not bad. It's reasonable. Can somebody talk me through a lower sum? Let me see. Emma, go for it. And give me all 4. What's the lower sum height of this first slice? 8, exactly. If you look at the 2 upper boundaries, it'll be either a height of 8 for the lower one or 9 for the higher. So it's just 1 times 8. Keep going. What about the next one? Another 8. It doesn't matter which side it is as long as it's lower. And then 1 times what? 5. And then the next one's actually kind of boring. 0, yeah. It just got crushed to death. So you take the lower of the two boundaries and use that as your height, even if it's lame. Go ahead and add them up. Yeah, looks like 21. Does that make sense so far? So, and again, that's going to be too low, but it's reasonable. Is that okay so far? See how we did that? All right. Now, we got these numbers 99850 by looking at the graph. I marked them already, and we knew the parabola pattern. What if you get stuck? What if you say, I genuinely don't know how high this is?
You plug it in.
Yeah, assume that x is equal to 1. If x is equal to 1, then y is equal to what? Or you can actually plug it in. 1 squared is 1, times negative 1 is negative 1, plus 9 is 8, which is exactly what we expected at 1. So if you ever need a height at any given point, just plug in the value of x. It'll give you the value of y. Trapezoid sum. How do you do that?
You add the two and then.
Right. You average these. You can probably even do it in your head. What's halfway between 21 and 31?
26.
26, right. So it's 31 plus 21 over 2. So it's 52 divided by 2, which is 26. That, by all estimates, should be much more accurate. This should be very close to the actual answer. Probably not exact, but pretty close. Grab your calculators. You'll need them. Unless you can do halves in your head, which is possible. It's not like utterly beyond human capacity. So, how do we do this? How do we get the height of the first slice? You get a height by plugging in the value of x.
Right.
But what value of x do you plug in?
0.5.
Negative a half.
Negative.
Exactly. This is, if I want to be fancy, I would say 1 times alpha of negative a half plus 1 times alpha of what? What was the height? How do you get the height of the next slice? How do you plug it in?
0.5.
Oh, 1 half, 1.5. Plus 1 times alpha of what?
1.5.
1.5, or 1.5, or 3 halves. Plus 1 times alpha of what?
2.5.
2.5, 5 halves.
So 2.5.
Yeah, and if you're punching into a calculator, it doesn't care whether it's a decimal or not. I like fractions just because I do. And because they're usually more friendly. But I gotta get a cat here, I don't know math again. So, let's do it. What happens when you plug in negative a half? I want to do at least 1 in our head. What's negative a half squared? What's negative a half times negative a half? 1/4. Does that make it negative? Yeah, negative a fourth. Plus 9? 8 and 3/4. And we can do that as a decimal. 8.75. Plus, what about if you plug in 1 half? Anybody?
9.
Well, plug in a half, squared is a fourth,
Oh, the same
take it negative. It just turns out, by luck, to be the exact same thing. 8.75. Plus, here's the thing that's interesting, 3 halves. What's 3 halves squared?
9/4.
9/4. Make it negative.
Negative
Negative
9/4.
9/4. I think that's negative 2.25,
Yeah.
I think. Add it to 9.
6.75.
6.75, yeah. Plus, now 5 halves squared.
25/4.
25/4.
Oh my.
That's 6.25.
6.25, so it'd be
Make it negative.
2 negative 6.25.
Yeah. And then add it to 9.
2.75.
Got it. Let me be so kind as to add those up. 8.75 plus 8.75 plus 6.75 plus 2.75. I do the whole numbers first, 8, 16, 22, 24, 25 and a half. I think you got 27.
Oh, wow.
The trapezoid and midpoint sums are much more accurate than the upper and lower sums usually. So we can be pretty confident that the real answer is somewhere between 26 and 27. To get a more accurate answer, use more slices. But for the purposes of the assignment and for the purposes of this test that's coming up, we're going to use a reasonably tame number of slices. I'm not going to say, do 47 slices. First of all, that would be a lot of slices. And number two, can you imagine dividing this by 47? So you go 4 over 47 spaces over and find out what the height is there. Wow. So, well, what is -1 plus 4 over 47? Negative 43 over 47. Yeehaw, I'll plug that in here, square it, take it negative. No, I'm not doing that to you. Let me double check
I would
something.
take the whole test.
Yeah, you're sick. You just get like 5 slices. Woohoo, I got my first slice. Good. Get the other 47. What? Let me check. I think I might have a replacement homework. Because I think the homework on this is really lame. That was 5G.
Lane by easy or lane by hard?
Lane by lane. Aha! I thought so.
No, lane by a person who can't walk.
Homework can't walk. Everything carries a one person.
Yes. Let me print this off because I looked at the homework in the book and it's awful. And Ella, if you're listening from home, which you probably are, I'm going to post, I'll email this to you.
Right now.
Chicago does email.
I'll email it to you in a little bit. But I'm printing this off as we speak. The book has this nasty habit of picking this random number of slices, like 8 or 7 or something like that. And it says, well, this would be easy to do. Let me show you what I mean.
Liam broke up with my with fruit snacks.
Yeah, like for example, they said make sure to use 4 slices even if the width isn't 4. Like if the width is 5, use 4 slices anyway. If the width is 7, use 4 slices.
That's a lot of
And I think that's cruel. So I will use, pretty much on the test, I will pretty much guarantee that you'll have a width of 1 on the slices. Why? Just because I'm feeling merciful.
Wait, so are you gonna have like tell us how many slices we need?
Yes,
Okay.
I will tell you. Like n equals something, and that's
That
the
would-
number of slices.
That would kind of change the answer every time if we all pick different slices. I guess.
Correct.
You
If you have more slices, it'll actually be a more accurate answer, but it'll probably be a nightmare to calculate. That's actually why calculators and computers are really good for this. If you tell the computer, use 5,000 slices, it can do 5,000 slices in, it takes a millisecond longer to do 5,000 slices than it does to do 5. So computers are excellent at this stuff.
So is there a way to find the exact?
Is there a way to find the exact area? Interestingly enough, yes. And I think it's time. The book doesn't exactly want me to tell you yet, but I'm going to. So everybody get this? I could just have Al out and say, no, I haven't written it down yet. I can't hear you. Did you say? No, I guess no objections. But anyway,
You can just pause it.
this is a quick I think I summarized these already. Oh, that's right. You can pause it. You can rewind. I didn't tell you what these are. Left sum and right sum. Left sum is when you use the left-hand side for the height all the time, whether it's high or low. So it's actually pretty easy to do. It's just you would use 8, 9, 8, 5. Does that make sense? You'd use the left-hand side of each slice no matter what. So it's actually easier than using the upper sum. The upper sum, you have to, which one is bigger? Here you just say left, 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 left. Any guesses what the right sum would be?
The middle sum.
Yeah, use the right-hand side as the height, no matter what.
So for like -1, you just use 8, and if you're doing the left sum?
Oh, if you're doing the left sum, yeah, you would use 8.
Okay.
Then for the next one, you'd use 9. Then for the next one, you'd use 8. And for the next one, you'd use 5. Do whatever the left-hand side
So for
whether
this
it's
one,
big
it'd
or
be the
small.
same?
What's that?
For this one?
In this particular one, it just
Yeah.
happened, it would
Yeah.
happen to be
Because
this.
he has the-
Although, it should be a little different, because this was 9985.
Oh, it'd be 8, 9.
It would be 8985 if you use the left-hand side. Here, which one's higher? 9. Which one's higher? 9. Here, which one's left? 8. Which one's left? 9. Does that make sense? So computers find these much easier to calculate. Because if you have the computer have to figure out which one's higher every time, you slow the computer down. Here, you just do left, 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 left. It just goes through there the fast enough. Actually faster. So, what is Simpson's rule? I forgot to tell you that. This was actually kind of fascinating. It came years later after this, after Riemann. Simpson was refining Riemann's work, and he discovered, he was trying to think, is there any way to get a better estimate using the same number of slices? And we found out that using trapezoids is much more accurate than using upper rectangles or lower rectangles. Does that make sense? So is there another shape, another geometry shape that we could use that would be even better than a trapezoid? Because it turns out the answer is yes. Watch this. I'm going to use this as an example. Guess what he's using?
Parabola?
He's using slices of parabolas.
What?
Oh, lordy.
How does that work?
He just throws away the rest and just uses a parabola slice here.
But how do you find the?
Excellent question.
What?
That was the first time I ran into this was at college, I was taking calculus in college. And my eyes, I'm sure they got as big as saucer plates, and I was just like, I knew how to graph parabolas, I wasn't an idiot. But I said like, slice of a parabola?
That's a parabola.
What is it? Yeah, what's a parabola, professor? Get out of here.
Mr. Pound.
Do you notice we'd have different parabolas for every single one of them?
Oh, yeah.
Oh, wow.
You'd have another parabola that would go like this for this next one, another one that goes like this for the next one. You'd have to use 4 different parabolas and take a slice of each one. This doesn't sound fun.
No.
Yeah, no thank
It turns out he did all the heavy lifting for us. By the way, please pray for Simpson, the repose of his soul, because we owe him a great debt of gratitude. Simpson's rule does
you.
this.
Pray for Riemann.
Here's a quick question. Let's just say here's a typical slice of a parabola. Like here's a parabolic graph, and the area under slice. Now, do you notice there's endpoints and then there's this middle thing?
Like the vertex?
Kind of like a vertex. It might not be the vertex, but it's close. Does it make sense? Like, picture in real life. If this is like a thin sheet of metal, is there any realistic way you could get it to do this? Like, you put a really thin sheet of metal and balance it over these two ends. What would you do to get this thing to bend like this? Just physically.
You like down.
Yeah, push down on it or put a weight
Right.
in the middle. Does that make sense? So in your estimate, which one has more weight? Is there more weight on the edges or in the middle? It's apparently in the middle. I mean, hopefully these are tough walls, but. So there's more weight here. I would say 2 times more weight. At the midpoint. Than at the edges. Now, how did I get 2? I'm plagiarizing since he did all the work.
Cheapo.
Now, the reason I say this is because it'll make the formula make a little bit more sense. The Simpsons, SS is for Simpson's son. That's a little awkward, especially after studying World War II. The Gestapo. But he's the math Gestapo. Here's what it is. You remember how
The Gestapo copied it.
to get a trapezoid sum, you average the upper and lower? You're kind of going to do this. You're going to take the 2 best sums, the trapezoid and midpoint sum, and average them. They kind of make sense? The trapezoid sum and the midpoint sum, if you average them, they at least should get a fairly accurate answer, because both of these are pretty good. But they're going to weight one as being a little stronger than the other. Guess which one has more weight?
Trapezoid.
The midpoint or the trapezoid? The trapezoid goes from end to end.
The midpoint, yeah.
Yeah, the trapezoid goes from end to end here. The midpoint has more weight, twice as much weight. Here's what you do. How do you average three
So
numbers?
you do it twice. So you
Yes.
do midpoint plus trapezoid divided by 3.
Midpoint sum plus trapezoid sum divided by 3.
Is that always the case?
Yep.
Okay.
That will automatically get you parabola slices, believe it or not. And Simpson proved that.
Really? Wow, that is
And we don't have to worry about all the grunt work of how to
Yeah,
prove
that's
it.
not, that looks horrible.
We just say, glory be to God for giving us Simpson. Thank you very much. Thank you, rest in peace.
Right. Thank you.
And that was just nice. So it's a triple average. You just make the midpoint twice as heavy. So it's relatively easy to calculate too. In this case, the Simpson's rule, I just abbreviated SIMP. The midpoint was 27. So 27 plus 27 plus 26, all divided by 3. So in this case is 80, I think, divided by 3. So, or, what was that, 26 2/3. That's Simpson's rule estimate of what the area is. Any questions so far?
Nope.
I'm going to give you a teeny teaser, by the way. You should not know this yet. The book wanted you to discover this. By the way, I'm stalling for the worksheets to print. What shape was this graph that we actually used?
Parabola.
Parabola. What kind of slices are we using with Simpson's rule?
Parabola slices.
Parabola slices.
You could find the exact.
This will give us the exact area.
Oh, wow.
By the way, we're just lucky enough to have a parabola. If I had some sort of wacky graph, like something to the 4th power, no guarantees. But if this is a parabola, and we're using parabola slices anyway, they're going to match perfectly. That's just by accident.
Wow.
So I can pretty much tell you on this one, the exact area under the curve is 26 2/3. Now you might be asking, is there a way to get the exact area even if we don't get lucky? The answer is maybe.
Ooh, that teaser. ...
To be continued. Just a second, I'm gonna grab the worksheets. Either they didn't print or somebody swiped them, which has happened. Some people saying, oh my goodness, I printed off 17 copies of my Declaration of Independence or something like that. And they grabbed my 10 copies of calculus underneath by accident. Okay, so I'm printing it again. It's claiming that it just printed. I will see if it's lying to me.
Should we end this recording?
I don't know.
I see what happened. They, somebody nicely actually put it off to the side and picked up their copy.
Okay. You
So
get
I
two
guess I have a
copies?
double copy.
Oh.
I'll have some copies of myself to enjoy. So, and now I will be posting this by email to you. Voila.
Yeah, this is.
Now, number 1, I'm letting you graph on your own. Hopefully that's not too tough. This is probably the dumbest example I could possibly give for Riemann sums. It's a graph of a line. So you wouldn't need Riemann sums for this. You could just do triangles and such. But do it anyway. Your assignment, so this goes to 1, 2, 3, 4, and 5. I would like you just to do I'm not having you do the whole thing.
I see where you actually did that.
We're only doing a little bit.
Yeah.
It's homework 5J. This is a worksheet. I just want you to do 1, 2, and 3. And I want you to skip the exact area. Because we don't know how to do that yet. I did, by the way, have a spoiler there, which implies it's possible. Otherwise, I wouldn't ask you for it. Wednesday. So just 1, 2, and 3. So do upper, lower, and in each one of these, make sure it's 5 slices. That's why I say 5 upper sums, 5 lower sums. I don't mean to do it 5 times. So that's probably was a bad way to put it. But each one is going to have 5 slices. I made sure that it actually came out equal. Okay? So, and Ella, I will email this to you post-haste. You can try your luck at this. Just one, I'll just write it on here. This is homework number 5J, worksheet. I hope you can read this. Just numbers 1, 2, and 3. And do not
The
do the
line.
exact area because I haven't showed it yet. Okay? So graduates, call me over if we get stuck. Except Ella, you can't call me over, but, you know. We'll talk to you later. Bye.